we move on to the next stage in our study, that is differentiating scalar-valued functions of a vector variable. So first let me make some notational remarks. Throughout, U subset of Rn will be an open set. And I will not pre-specify what the dimension n is. It's a fixed number greater than or equal to 1. Whatever I'm about to say also applies for the case n equal to 1. So our aim is to now study a function f from u to r, more precisely to study the differentiability of such a function. Now the first question that arises is, how do we define differentiability in this situation? One complication that arises is because we cannot divide by a vector. The natural thing to do would be to consider a Newton quotient, just like what we did in the one variable case, and consider something like this: f of x plus h minus f of x by h. Only issue is this is simply not possible in higher dimensions because h is now a vector. So what do we do to fix the situation? Well, recall that when we define differentiability in the one variable case, we had done a brief description of the derivative as the best linear approximation of the function. So recall that in the one variable case, f is differentiable at x in u if and only if we can find L a real number and E a function defined from V to R. 0 is in V and V is some open set. Such that f of x plus h is equal to f of x plus LH plus E of h, where we have E of h by h goes to 0 as h goes to 0. So this just says that if a function f is differentiable at the point x, then you can make a good linear approximation, or rather more precisely an affine linear approximation. This part f of x plus LH is supposed to be the affine linear part, and this is an error term, and the error term is small. The smallness is quantified by the fact that E of h by h goes to 0 as h goes to 0. Okay, now we are going to mimic this definition exactly. The key observation is the fact that the map h going to LH is a linear map in the one variable case. Multiplication by a scalar is a linear map in the one variable case. So this allows us, this viewpoint of the derivative as the best linear approximation allows us to define the derivative of a scalar valued function of a vector variable. Let's do that. Definition. As I mentioned, throughout f from u to r will be a function and u will be an open set, so I'm not going to write that in the definition. We say f is differentiable at the point x in u, if we can find a linear functional L from Rn to R. Linear functional is just another specific term for a linear transformation, but taking values in the base field, which happens to be R. Okay, and a real valued function E from Rn into R such that actually the E is not from R into R, E is from V to R, where this V is a neighborhood of 0, where 0 is in V and V subset of Rn is open such that f of x plus h is equal to f of x plus LH plus EH, and E of h we cannot divide by the vector h, but we can take the norm. E of h by norm h goes to 0 as h goes to 0. Okay, so the first question that should come to your mind is, what is this norm in the denominator? Well, it really doesn't matter. All norms on Rn are the same, but whenever I consider the Euclidean space Rn, I'm going to be considering the Euclidean norm, and similarly I'm always going to consider only the Euclidean metric on Rn. Okay, so you divide by norm h and this should go to 0. Okay, E of h by norm h should go to 0. Now if you look back at the definition on the last page, which I have written here in the one variable case, and look at this definition here, both are identical. So we have just taken another formulation of the derivative in one variable and just declared that same expression to be defining the derivative in higher dimensions. So the map L is the derivative. The map L is the derivative. And we denote this by dfx. We denote this by df of x. Okay, so the derivative in this scenario is modeled on our observation that the derivative in one variable is the best linear approximation. So let me just make some remarks. So the first remark is, we have assumed x plus h is in U, right? So recall that the function E is defined on some open set that contains 0. Okay, we are assuming that x plus h belongs to U so that you can actually take the f on that. So this just means x plus h belongs to U when h is in V. This can be guaranteed because U is open. So h is defined on some pre-specified open set V. We can shrink that V if necessary to ensure that x plus h is always an element of U whenever h comes from V. This is not such a major issue. So the second remark is more interesting. Now when we define the derivative, we are considering quotients of this type, E of h by norm h, because we are unable to divide by vectors. So why did we do this complicated stuff about linear approximations and all? You could have just considered this Newton quotient, f of x plus h minus f of x by norm h, and taken h to 0. What would happen in this scenario? Would this give the derivative? Will this give anything meaningful? I want you to think about this. Why didn't we just define the derivative using this modified Newton quotient? Okay. Let me make one more definition, because we are going to be dealing with this error function frequently in the proofs, and we have to discuss the behavior of the error function as h goes to 0. Let's make a convenient definition for this. This is the definition of a sublinear function. sublinear function. The definition goes as follows. Again, E is from U, or rather V to Rm this time. It really is, I'm not requiring it to be taking values only in the real numbers, where V subset of Rn is some open set that contains 0. I don't really care. Some open set containing 0. Containing 0. Okay. We say E is sublinear. We say E is sublinear if, as you can expect, E of H by norm H goes to 0 as H goes to 0. Okay. So we are going to use this notion of sublinear often in proofs where we have to deal with these error functions. And I mean, this having a convenient expression for such functions will simplify the proofs. So immediately start with the first proposition, and this is an important proposition to prove, though the proof is rather trivial. It's the fact that if f from U to R is differentiable at x in U, then the derivative is unique. You cannot have two different expressions parading as the derivative. Okay, so the proof of this is rather easy. Proof: let L and M be two linear functionals that satisfy the definition of the derivative. Definition of derivative of f at x. Okay, so we can find corresponding functions, corresponding sublinear functions E1 and E2. Okay, what this means is that f of x plus h minus f of x is equal to LH plus E1h, where E1 is going to be sublinear. It's also equal to MH plus E2h. Okay, this just means that LH minus MH is equal to E2h minus E1h. Rather straightforward algebra. Now this is true for h close to 0, right? Why close to 0? Because we want x plus h to be in U, right? Now let E1 to En be the standard basis. For Rn. We want to show that LEI equal to MEI. That will show that L equal to M, because a linear functional is completely determined by its behavior on a standard basis. Now x plus E1, x plus E2 and so on may not be in U. So what we do is we scale. Set h to be T1 t greater than 0 suitably small. How small? So that x plus Te1 is actually going to be in the open set U. Okay. Now observe that you have LTE1 minus MTE1 is equal to E2 of TE1 minus E1 of TE1. That's just the last line where I have substituted the specific value for h. Okay, now since t is not equal to 0, we can divide both sides by t, and because L and M are both linear, I can take this t outside in both, right? So dividing by t, I will get LE1 minus ME1 is E2 TE1 by t minus E1 TE1 by t. Right? Now the left hand side is independent of t, so when you take t going to 0, the left hand side is going to remain unaffected. The limit will exist and the limit will be equal to LE1 minus ME1. What about the right hand side? Well, let's just look at one term. Just focus on this. We know that E2 TE1 by norm TE1 goes to 0 as t goes to 0, but since we are in the Euclidean setting and E1 is a standard basis vector, norm E1 is just 1. So this just immediately gives that as t goes to 0, E2 TE1 by t goes to 0. And the same remark applies for the second term. This term also goes to 0 as t goes to 0. Net upshot is LE1 minus ME1 is 0. There was nothing special about E1. The same proof works for the other standard basis. So in fact, this concludes the proof that LEI equal to MEI, which just means that L is equal to M, because our linear functional is determined entirely by its behavior on a basis. Okay, so the derivative is unique. So let's see some examples of differentiation. We will see more in the next video where we talk about the gradient, but for the time being, let's set the stage and consider just at least 2 examples. Suppose f is constant. Suppose f from Rn to R is constant. Then f is differentiable at all points x in R, of course, all points x in Rn, and as you can guess, dfx is going to be 0, is the 0 functional. Why is this? Well, this should be obvious to you, but you can just write down and see this also. F of x plus h is f of x plus h minus f of x is just 0. So we can just take the 0 functional and the error function to be also the 0 function, and we would be done. Okay. Second example is equally trivial but somewhat more interesting. If f is a linear functional, if f itself is a linear functional, then f is differentiable at all points of Rn, and dfx is just f. Okay. Now this is again obvious because f of x plus h minus f of x is just f of x plus f of h minus f of x, which is just f of h. So we can just take the linear functional f in the definition of the derivative and take it as the candidate derivative and take e to be 0 again. So in this case also f is differentiable everywhere, and the derivative is f itself, which is sort of to be expected because the derivative is supposed to be the best linear approximation, and since f is already linear, you don't need to approximate f. Okay, so we will conclude this short video by one more proposition, which is also easy. Proposition if f is differentiable at x in U, then f is continuous at x. Well, how do you prove this? Well, we know that f of x plus h minus f of x is equal to this dfx h plus e of h. Okay. Now as h goes to 0, the right hand side goes to 0. Well, the first term dfxh obviously goes to 0. dfx is a linear mapping, and the term e of h goes to 0 even after you divide by norm h and take h to 0. So without that norm h, it's going to go to 0 even faster. Okay, so as h goes to 0, f of x plus h minus f of x goes to 0. Okay, so this concludes the proof that the function f is continuous at the point x. So one final remark. So in the future, when we say f from u to r is differentiable, we will say such expressions. What this means is that f is differentiable at every single point of the domain u. Okay, so again, the definition of the function being differentiable at an open set just means it is true pointwise. Okay, now the next video is going to be about the gradient and an explicit way to compute the derivative. So far, this definition is not very useful in computation. The definition just tells you the characteristic property of the derivative. It doesn't tell you how to find out what this derivative is going to be. The next video will fix that. We will find an explicit way of computing the derivative using partial derivatives. This is a course on real analysis, and you have just watched the video on scalar valued functions of a vector variable.